This is the start of Chapter 4 of Make Electronics 2nd Edition by Charles Platt. The videos are going to cover 3 separate applications of our first integrated circuit, or IC, or chip, the 555 timer. And our first application is called the Monostable Multivibrator, or Monostable Mode. Now what I have in front of me is a disintegrated circuit made by Evil Mad Scientists, which is a company on the West Coast. They have created this disintegrated circuit. It's got 8 pins going across the top and the bottom, and it's made of familiar components to us, resistors and transistors. The actual 555 timer we're going to use for most of these lessons, however, is this small integrated circuit, which is simply that collection of resistors and transistors in a small, easy-to-use box. And it has, again, 8 pins, 4 on each side, and the orientation is the most important thing to realize at first. There's always a small divot at the top and another small hole where the first pin is, and your breadboard is made to take integrated circuits of these types called a DIP package or a dual inline package. You spread the legs to an appropriate width and you press them in so that it splits across the breadboard. You may find that your 555 timers actually require a little bit of slight pressing to get them to bridge just perfectly, and this is why the breadboard has that gap running up and down the middle so that you can connect all pins on each side of the integrated circuit separately, not short them out to each other, and then connect wires to all of those. Now note, in the Every Bunch Kit 3, you have 4 555 timers shipped to you, each of them with 8 pins. They're grouped together. There's a couple other integrated circuits as well, so make sure you use one that says 555, and that has got the 8 pins. I've oriented here the disintegrated circuit that I have from Evil Mad Scientist, showing the ground pin in the number 1 spot, there in the upper left-hand corner. And along the top, between the 1 and 8 pins, should be that half spherical divot. You should see that also on your chip. Both these are used to get the orientation. Now make sure that your pins are not missing the hole. They haven't bent or flailed out when you try to push it in. That all 8 of the pins slide nice and firmly into the breadboard when you insert it without bending or breaking. If you pull ICs a lot, you're going to eventually want an IC puller tool like my yellow-handed implement here that reaches underneath into that gap between the breadboard and lets you pull them out straight up and down. Wiggling them can be a recipe for disaster, as it's likely to bend pins. Let's take a look at this integrated circuit that, as I say, has been disintegrated or expanded till we can see its individual parts. Across the top of the schematic, you see 3 identical 5 kilo ohm resistors. They divide the incoming 9 volts from the power supply into thirds, specifically so there's 3 volts and 6 volts, and they get distributed to the other parts of the circuit. Now notice there's 5 parts in total: the threshold comparator, the trigger comparator, the flip-flop, the output driver, and then in the bottom corner, the discharge and reset. So let's look at the threshold comparator first. So it's receiving 6 volts from the series resistors, and that is represented in the schematic diagram by the yellow triangle B. What a comparator does is it compares 2 voltages and gives an output based on the difference. So if the input on the threshold circuit, which is 6, exceeds 6 volts, it will go high. Now the discharge, shown in purple, is comparing 3 volts to what comes in on the input or threshold. When A sees a lower threshold than the 3 volts, it goes low and it triggers the flip-flop, which is the third part of the 555 timer, and it's shown in green in the center of the circuit. The flip-flop is a really interesting element, and it's going to be the entire subject of 16B, which we're doing next, as the simplest logic memory unit. But it's essentially a switch which remembers its state and is set electronically. Now, the output driver is a series of transistors which, when the flip-flop goes positive, it drives a strong high current output pulse. out through pin 3, and when it's low, it cuts it all to ground. The final part of the 555 timer, schematically speaking, is the discharge and reset. Well, the reset we're going to be using today with the monostable multivibrator. When it is positive, it enables the timer to go, but when it's pulled negative by connecting it to ground briefly, it resets the flip-flop and has everything start from scratch. So it's a way of erasing the memory that was held in the flip-flop part of the circuit. My 555 disintegrated circuit is fully functional. It's got little clips to make up for the pins, and we'll see it in action next time. So here is the schematic which we're going to build today, the monostable multivibrator. As built up in Lush Projects, I've included in the notes the link to my version of the circuit on Lush Circuits. So let's count through the pins. Notice they're not in the same order, with the input voltage labeled VCC, the discharge pin, DIS, trigger with a bar over it, which would be not trigger, which is usually, and in our textbook is simply called the input. Then there's the threshold, the control, the ground, which, like voltage in, is fairly self-explanatory. The output, then, which is what we'll be viewing through an LED. I've also connected a output pin to the oscilloscope tracer running below. And then finally a reset pin, which basically just causes everything to start over. When you first plug the circuit in, it shouldn't do anything. Of course, no components should get hot. Nothing should burn out, but you shouldn't see anything turn on. And closing the reset button also should have no effect. The LED, which is what we'll be watching at, is only going to go high when that output does. And that is going to require both closing the trigger or input switch and adjusting the potentiometer, which is associated with that trigger to set a threshold level. Now that pot is going to have to be moved all the way over to one side before anything happens. Now notice that this thresholding pot is set up in a sort of classic voltage divider configuration, with one side connected to the high rail, 9 volts, and the others connected to the negative rail, or 0 volts. So once you've got the voltage on the switch down to sufficiently low a level, it will trigger the input, and you'll start to see the light turn on when you close that switch. Now notice the unique behavior of the monostable multivibrator. Every time you close the switch, no matter how brief, it gives you the same pulse duration out. That is because the discharge capacitor, which we'll get to in a moment, is a particular time constant, which also sets a threshold on the 555 timer. Now, if you hold that switch in too long, it will continue to stay on. If you turn the switch on just briefly, though, you'll still get a pulse of set duration out. Again, if you hold the threshold button in for longer than the duration of the set pulse, the LED will continue to stay on, but a brief touch will turn on for a fixed amount of time. All right, let's figure out how to change that amount of time. That requires using the second pot, which the textbook specifies as being maybe up to 500 kiloohms. I used a smaller one here to get faster time constants, so the simulation runs a little bit faster. I have decreased the resistance in that upper potentiometer, decreasing the time constant, and now I'm able to decrease the pulse duration. If you look at figure 417, there's a chart of the capacitance, currently with a 15 microfarad capacitor on our timing capacitor, and resistance selected by that potentiometer. So you read off the resistance and capacitance in the rows and columns of the chart, and the numbers in the chart tell you the number of seconds that the monostable multivibrator should give you an on-duration pulse. Using the potentiometer lets you just to adjust the total resistance. Note the unique conformation of the potentiometer. The bottom part of the pot is actually looped up to the center pin. So we have the fixed resistor, 1K in my case, plus then the variable resistor that slides up and down, and that tells us how much the total resistance is going into the RC network, which determines how long until the threshold condition is met on the threshold pin, which is what turns the timer back off. Notice again that turning on means going high in voltage, up to almost 9 volts out the output, and also lighting up the LED. Let's look at the reset switch now on the other side. So I mentioned earlier, the reset switch basically turns everything off. So if we have closed the first switch, or holding it down with our finger, and then we're tapping on the reset, we'll see that there is no wait. It simply goes on and off at our command. Again, with the resets open, the monostable mode means we get pulses of fixed duration, whereas on the reset pin, it toggles on and off just as fast as we touch that upper switch. One of the uses then of the timer in the monostable mode is to so-called debounce switches, or take a switch that might rattle closed and make sure that it stays closed effectively in a circuit for a fixed amount of time. All right, let's start looking at building the circuit. Here we have the circuit diagram, figure 411, figure 412. The way to build it, I tried to do a very faithful replication in most of the colors, lengths, and positioning of the wires. Feel free to do something different, but again, it's easier to sort of follow the book the first time. And so I'm just going to lay my built circuit right on top of the example from the textbook. I'm going to start with playing with that threshold. As the textbook, you have to kind of move it around and get it to the point where I actually see the LED fire once I press the trigger button. There I am. I seem to have found the moment, put it, the point which is required to hit the threshold. And I'm going to leave that lower 20 kilo ohm pot in a position where it stays on reliably each time. Now let's play with the duration potentiometer. Again, the values on the duration pot are really determined by the chart in figure 417, which gives the time constants for given resistor and capacitor configurations. As I go to larger and larger resistances on a pot, I get a longer time, as shown now with the LED turning on. The reset, however, immediately turns the LED off. Without waiting for the time to complete. If I hold the trigger down, then tapping the reset will simply turn off the LED. But if I'm not holding the trigger, the reset will permanently turn it off. Very similar sort of to the operation of the relay latch in the past experiment. Tapping the trigger multiple times during the LED on time has no effect. I actually have to hold it down longer than the LED time to get a prompt release when I let it go. Spend some time playing around with the behavior of the circuit. We're going to end today with doing a little bit of practice of following circuit diagrams on schematics and breadboards. Let's start with the part of the circuit which sets the time constant for how long the pulse stays on. So down from the rail, we go over through a 10 kilo ohm fixed resistor and then into the 500 kilo ohm pot. Now I've used a 100 kilo ohm pot in my particular circuit. Note how one end of the pot is looped around to the center pin, and then it goes into pin 7. Pin 7 is the discharge. So that determines when the discharge goes low, when it is that the circuit fires with respect to the 15 microfarad capacitor charging. Changing either the capacitor or the potentiometer setting will change how long the pulse goes on to. Remember that 15 microfarad capacitor has electrolytic and has to be properly attached. Now the power for the circuit comes of the difference between the ground, which in this case is running all the way through the bottom of my breadboard and back up, ending up on pin 1. Notice how I've simply jumpered over with a black cable to the ground, rather than across the circuit as shown in the schematic. Similarly, the red, using the fact I've got 2 power buses on each breadboard, simply runs across on the right side of the circuit up to the battery. All right, now let's look at the trigger or input. So we start with a fixed 10 kilo ohm resistor, and that splits. Part of it goes right into pin 2 being the trigger or the input, and the other part teeing down through the push button A, the one we press to trigger, into the 20 kilo ohm potentiometer. Other sides are set to both ground and to 9 volts. Next, we'll look at the fixed 10 kilo ohm resistor that goes into 4, the reset. This is the reset pin, which is B. It has to be held high. We call this a pull-up resistor. That first 10 kilo ohm resistor, it's pulled up to 9 volts unless the pin is pushed. If the pin is pushed, then 4 goes down to negative. When it goes negative, that's when the reset happens. We don't have to worry about short circuit because of that 10 kilo ohm resistor. This use of a pull-up resistor to keep a pin at a fixed value is very common in integrated circuits. In general, with ICs, every pin should be connected to something. Now let's look at the output, or pin 3. Output's very simple. It goes through a current limiting resistor, which we choose again to be 470 ohms, and I get a nice bright LED light, which is connected to ground. Of course, make sure your LED is in with the correct polarity. Finally, as described in the textbook, we need a very small capacitor. We use 0.01 microfarads on pin 5, the control. This is to make sure that we start up in the correct state. Again, some unique aspects of the circuit include the way that the potentiometer is looped back from the outer pin on to the center one. That gives us just a variable resistor rather than a true double-sided pot that's used to set the time constant. And the way that the push button for the trigger is kept at a high voltage on pin 2 until the button is pushed, which lowers the trigger. Once it goes below a certain fixed level, the 555 timer is initiated. Build the monostable multivibrator circuit. Use the table in figure 417 to design a version that stays on for almost exactly 20 seconds, as close as you can get it. Pay careful attention to the warnings about resistor and capacitor values that are given in the textbook just underneath that figure. Put your calculations of what resistor and capacitance values that you should use in your logbook, and please upload a video of your 20-second timed LED running. Next thing I'd like you to do is to give 2 examples of a situation where you've encountered electronics in everyday life that behave like the monostable mode of the 555 timer. Your book gives several such examples, one of them being the intermittent windshield wipers in an automobile. Take the text for some examples and give me some examples where you think you may have seen this circuit doing things out in the real world. Finally, take a look at the principles of operation for the disintegrated 3/5 circuit from Evil Mad Scientist. That's in this link. Count the transistors that are used in a 555, either from that brochure or by looking at a still frame of the video. And then take a look online to estimate the number of transistors that are actually used in a top-of-the-line, say, gaming computer CPU. Think about the density of those transistors in the 2 different integrated circuits, and take a look at when the 555, the world's most popular integrated circuit, was invented.